Hello everybody, I'm going to present my project which is on the neural enemy transfer style for course EEL6825. So to achieve artificial intelligence, one of the important goals is to enable machines to create art pieces just as smart as human beings. So this is obviously a very challenging task. So why this is difficult? Because artistic creation of painting is not simply just by putting shapes and colors, mix them together to form a picture. So a good drawer usually considers several things before they actually started. So for example, how to arrange the composition of objects within a painting, how to use chiaroscuro to depict light and dim, and how to develop textures and use different colorizations for different objects, and how to use line shapes to give the outlook of an object. So every artist have different style for using these elements, and sum them up, we get something called style. And basically, if we want our machine to learn how to draw, we first need to train them with all these kind of styles. So how to extract the styles? This is obviously a very difficult question. And recently, the developing of a neural network brings up a new hope to these areas. Among all form neural network, there is a particular kind of neural network, which is a convolutional neural network. And this have made a tremendous success in the field of image process. Like our visual system, the convolutional neural network does not process the image as it sees directly. And it will decompose the input into small pieces and process it along a hierarchy structure. And as we go deeper and deeper into the network, the content of the image is being summarized. And with different feature maps generated on different layers, we could not only detect the local features, but the high-level features of the artwork. So the convolutional neural network could be a powerful tool when we want to extract features from our image. So to achieve actual art composing for machines, so we must first to extract features from somewhere. And in this particular project, what I did is to extract features from some animation artworks and apply it on arbitrary images. And this could be an initial style to achieve artificial intelligence of machine drawing. So why we choose artworks of anime? So because basically the features of manga style are much more subtle than neural images. And if our machine can perceive these subtle changes and extract them, then it will be a great leap forward to our final goal of artificial machine drawing. So here I'm gonna introduce our implementation of our work. So the network we use is actually a VGG network, which is widely used in image processing area. And this is a network which composed of 16-way layers. Among all layers, there are 5 groups of convolutional layers. Each group of convolutional layers are connected by a 2x2 pooling layer. Within each convolutional layer, there are some kernels, which is 3x3, used as perceptive field. The number of convolutional kernels in each group rises from 64 to 512 as we go deeper into the network. And all the convolution layers are equipped with RELU as the activation function. In original VGG16 network, there is a group of fully connected layers after the convolutional layer groups. This is usually used for image classification. Since we are not going to use this part, we just disable them when we are implementing our work. And the next question is how to extract features from a convolutional neural network. Here is an example. As we pass the image through the network, we want to know which layer preserves what kind of information. And as we can see here, during the process, lower layer mainly keep the information as the original picture. But as we are going deeper into the network, the high-level layers becomes more precise on capturing the shapes and the skeleton of the objects. And this indicates we can extract content features from the image in higher layers. And to extract the style features is much more complicated because the style image is not only included in the skeleton of the image but also on every tiny parts. For example, the adjacent pixel difference could reflect how the contrast hue is being treated by this artist. Thus, to obtain the style features, we have to consider the overall picture and we have to consider multiple convolutional layers together. So this is basically what we did to obtain our output. So by using a content image, a style image, and initially a blank output image, we try to find an image which have the smallest difference between the content and the style. And in the actual implementation, we treat the loss between the output and the content and the loss between the output and the style separately. And we add weight to each term. So this means we can adjust how much we want from each part. If we want content more or if we want style more. So the content loss is usually very easy to calculate. After we extract the content features, we compare the pixel difference between the content and output, and we use some square error to do our optimization. So as we stated before, to calculate the style loss is much more complicated. To consider the overall picture, we must use a technique which is called the grand matrix. So how we obtain this is first, from the feature maps, we flatten the feature map into a one-dimensional vector and use the inner product of this vector with its transpose to get the grand matrix. And after we get the grand matrix of our output and the style, we see the difference between them and normalize it. And within this layer, we get the loss of style. And since we have multiple layers, we have to sum them up with specific weight. But in actual implementation, we treat each layer equally, so all the weights are set to 1. And this is what we got. So we found that with 8 gigabytes and the CPU-only computation, to process an image of 500 times 500 pixel size usually takes about 10 minutes to finish one optimization cycle. And usually, the loss will converge within 10 optimization cycles. And we can monitor the change of the picture as we are trying to optimize it in every cycle. And as we can see more and more content features are applied in our output image. And meanwhile, we have some style, like sketch features which are come from the style image. We also studied how different kind of factors will affect the quality of our output image. The first thing we consider is the method of pooling. So between each convolutional groups, there are pooling layers. So the max pooling and average pooling will cause difference for the quality of the output image. And in the first experiment we did on this aspect, we use a style image which is not highly colorized. So we can see how these poolings could affect the line styles and some kind of texture styles when we want to transfer it to the content image. So as you can see from the result, this is our result obtained from max pooling, and this is the result we obtained from average pooling. So by max pooling, the lines and shapes of content image is very well preserved. The curvature on the lines and somehow reflects the way we painted in the still picture. Well, the image obtained by average pooling show less contrast and the boundary of the objects are much smoother. In the second experiment, we apply the same parameter, but this time the still image is heavily colorized. So we could see the different method will affect the color and the hue of the output image. The max pooling gives us an output image with a lot of color fragmentations, and the color transition in some local areas is very abrupt. The average pooling gives us an output image with milder change of colors, but preserve less features than max pooling. The second factor we're going to talk about is the sampling from different layers. So by sampling of the content features from different layers, we can obtain different effects on our output image. Well, this shows we use 3 different kind of layers to extract the features of content. When the content is extracted from the second convolutional group, the output image preserves the information of content image very well, but there is not so much contrast, and obviously there is not so much style being transferred into this image. And when we are trying to extract the content from the first convolutional group, the output image is heavily blurred, and we have a serious loss of information in the content image, although the style seems to be expressed much stronger. When the content layer is extracted from the third convolutional group, we see to reach a balance between transferring the style and preserving the content information. The third factor we look into is the influence of the weight between content, the weight ratio between the content and the style loss. So as we stated before, the ratio weight between content and style loss is to measure how much we want for 2 features in our output image. A large content style weight ratio will cause a loss of style being smeared out during optimization. So here, as we can see, by using different weight ratios, we are decreasing weight ratios in this direction, and when we are processing it with less weight ratios, we add more style features to the output, but the loss of content information become higher. At 10 to the minus 3 level, the information of the content is still well preserved, but when we go to an even smaller level, there is a drastic trend of losing content features. At around 10 to the minus 4, the loss is so heavy that output image is almost smeared out. So this method also have a lot of shortcomings. So here I show 2 examples that we didn't get any good result. In the first experiment, we tried to apply the style from very simple drawing to content image, but CNN failed to capture the features from the simple line drawing. And in the second experiment, we tried to apply the style from a strongly contrast image to a photo. When the content weight is low, we can not distinguish anything from the output image. The shown picture is obtained by adjusting the weight ratio of content loss and style loss even to 1:1, and the combination image is still heavily blurred. So to sum up, we present an algorithm which can intelligently transfer some enemy artistic styles, and by adjusting different parameters, we can obtain output image with different features. The shortcoming of these algorithms may provide useful information when we are trying to dig deeper on the question what the style of artwork really is.